All right. Hello, this is Physics 2211 Lab 3. This is the black hole in orbits experiment. Let's get right into it. All right. So just to start out, there's no actual experiment for this lab. It's just split up into two parts, both of which are solely coding. The black hole orbit code uses an elliptical orbit to calculate the mass of a black hole. We know the direction of the orbits, and just through calculation, we can find the mass of the black hole at the center. And then the planet and moon ship orbit delves into the three-body problem and how multiple objects can interact with each other in space. Now, the model for both of these simulates the interactions calculated by Newton's second laws uh, with kinematics and the universal gravitation law and all of that. So for the results, this is for part two. Part one was pretty simple. We'll see it a little later. But for part two, the final orbit was pretty erratic of the three bodies. This is the planet in the center, and then there's the moon is this teal orbit, and then the spaceship is the magenta orbit. And the ship was indeed interacting with both objects, as you can see, because if it was just interacting with the planet, it would be a simple elliptical orbit, and if it was just interacting with the moon, it would kind of spiral around it like that. But at the beginning, you kind of see it starts about here, and it kind of does go like this a little bit, and then it gets into an orbit in here, and then it gets shot out and orbits around here. So you can see that it's pretty erratic and is being influenced by both objects. Now, for the simulation code for part one, this is just calculating the parallel component of the net force, which is equal to the parallel component of change in momentum. Um, so yeah, so that is going to be used later. There's also perpendicular components that we have to use to calculate, but those are also in the code. And then this is kind of the final step where we calculate the radius squared, pretty simple, and then we have the net force due to it being equal to the change in momentum, and we have the speed. So we solve for the mass of the black hole, big M, and then we just print it out at the end of the program. And then this is done a bunch of times at different points in the orbit, and these values are about averaged out, and is a pretty useful application of universal gravitation. So now for part two, this is the data that I finally used to get that graph that I showed earlier, and these is what we're changing in order to get this the desired path, which shows that the ship is affected by both objects. And yeah, so the ship, along with the other objects, are only moving in two dimensions since there's no the zero z component. And then this is done a bunch of times: planet to ship, planet on ship. There's a planet on moon, ship on moon, etc., etc. Just defining the net force and position using just the law of universal gravitation for each of the objects. And this is again repeated a couple of times for all of the objects. And then this is the important part, which is updating the velocity and the position, which then get plugged back into here. This is an iterative process uh, over this delta t time step. So yeah, and the planet is stationary, therefore the velocity and position are not changing because, for all intents and purposes, there's no forces acting on it because the gravity force that the ship or the moon are going to act on it is very negligible compared to its large mass. Now for part one, just a simple elliptical orbit. And then down here you can see the outputs for the mass, roughly 1.7 times 10 to the 34th kilograms. And yeah, so as the model progresses, it gets more and more accurate as you take the average. And yeah, it's again that 1.7 times 10 to the 34th number. And then for part two, the ship orbits the moon for a little bit. You can kind of see it goes like this, and then it orbits around the moon a little bit. See, it kind of does that a little more, and then it eventually balances into an elliptical orbit or a couple of different elliptical orbits. But it is influenced, by the moon because it's not just one ellipse. So it's definitely influenced by both objects, and that's kind of what we were trying to do. So now, just finally, some further questions. What if we considered the full system of part one and part two combined, where there's the ship orbiting the moon and the planet, and then the moon orbits the planet orbits the star, and the star orbits the black hole. Now, the interactions will likely remain relatively constant since these objects will probably be pretty far away from each other. Like the ship, moon, planet system would probably be pretty far away from the star, which is already pretty far away from the black hole. So the planet and moon ship system would probably orbit roughly the same as it would normally. And then in part one, change of momentum and net force are essentially interchangeable, but they're calculated differently usually. The net force is used by universal gravitation, and the change of momentum is by velocity and time. So yeah, that's kind of it. So yeah, thank you for watching.